Hey everyone, welcome back to another episode of the QRL Show, the place where you come for the crypto and stay for the quantum. On today's episode, myself and Michael Strike from the QRL team are joined by Olivier Ezratty and Bob Sutor, and we're going to be having a post-quantum panel discussion. Both of the guests today have some really nice overlap in terms of both backgrounds, a deep history in quantum technologies. They're both authors as well, speakers, and myself and Michael are real excited to have them on today's episode. From a high level, Olivier is an author, trainer, advisor on quantum tech, works with both businesses and public services as well. He wrote the open source book, Understanding Quantum Technologies, which continues evolving. You can get it for free. We'll leave the link in the show notes, and it's currently in its 7th edition as of late. He's also the coordinator of quantum engineering elective at EPITA and a trainer at CEA. INSTN, and an independent expert for BPI France and Agency Nationale for Research. Pardon my pronunciation there. He's also the host of two quantum podcasts, and they kind of have two different focuses. The first is called Quantum, which kind of covers a general corpus of quantum news, and the second is Decode Quantum. That's longer form interviews with entrepreneurs, researchers, and that's in partnership with French Web. To note, these podcasts are primarily in French, but you can find Olivier's work online just by typing his name out. And our other guest for today's quantum panel that we're excited about is Bob Sutor. And he brings a ton of decades of experience, IT industry as a tech leader, executive, keynote speaker, author, advisor. He originally was a theoretical mathematician by training, PhD from Princeton, undergrad, wearing the crimson red at Harvard. And he is the VP and practice lead of emerging tech at the Futurum Group, helps a ton of large clients and investors better understand the complex tech that is quantum, AI, and he helps communicate that effectively. He is also, and this also lends well to his work as an author, he's spent several decades at IBM Research, where he either led or was part of efforts around AI, quantum computing, blockchain. And just like Olivier, Bob is also the author of a quantum computing book called Dancing with Qubits. And this came out originally in 2019, but the second edition came out earlier this calendar year. And lastly, Bob is an adjunct professor in the CS and engineering department, and I'm intimately familiar with the university, which is the University of Buffalo in Buffalo, New York. And I think I'll let each of our guests fill in the holes on their backgrounds and careers to really do it justice. But two areas or the main area where I think our audience is really important for them to relate to is both of you guys, Bob and Olivier. Not only do you understand the technology deeply, but you do a great job helping concise, condense, and make that complex technology more digestible to a broader audience, which is really helpful. Especially it's powerful in getting people to understand why it matters. So throughout today's conversation, I'm excited to kind of unpack a few of those things. To start out, Bob, Olivier, would one of you guys like to start out, fill in any holes on your background, and then we can jump into this panel?
Welcome, guys.
It's funny because it looks like my experience is 6 years old, but I have 40 years of experience, but in
yeah,
different
yeah. I'd
fields.
let you guys fill in the
I
holes
was a
here.
software. Well, it's you don't talk about the whole stuff, but I have a software engineering experience, but it's from a long time ago in the late 80s. But then I had some commonality with Bob. I did my internship at IBM in 85. And I was for 15 years working as a marketer at Microsoft in France. So I've been doing both R&D, marketing, business development. And I decided about 20 years ago to come back to technology and science. And I would say that after having worked for about 5 years in the AI space, as well as an author and a speaker and trainer, I decided that quantum was an interesting field because it's so diverse, so rich from scientific standpoint, and so dynamic that I found a new home.
Well, first, I would just say I was thinking as you were doing the introductions. Well, we're out of time now. Thank you for joining us. Once you And the thing is, once you've been in the industry, and I've been over 40 years, when people say, wow, you've done a lot, well, it's like, yeah, that's a good thing. I've been, employed for the last 4 decades, and I've been doing interesting things. So part of it for your listeners, that's that. One thing I will say, just relate to the Dancing with Qubits books, and the dancing part refers to a concept called entanglement. By the way, it's not just like Dancing with Stars and things like that. Was that really around 2018? I come from a math background. I could not find a reference that I liked. A lot of them assumed that you had 3 or 4 years of very intense physics, like quantum mechanics and things like this. And so part of it was, if I can't find a book I want to read, I should write that book, right? And maybe make a couple bucks. We'll see. But the other thing was just kind of opening this up to a larger audience. And I think Olivier and I both kind of try to do that. It's an interesting technology. It's going to be a very important technology. Unfortunately, I think most people spend way too much time in the weeds, right? It's almost like if I were going to write an app for my iPhone, right? But I first have to learn about transistors. You're not allowed to run, right? And all this low-level semiconductor stuff. And then you're allowed to write, your dating app for the iPhone like this. And that's how quantum almost seems at times. So we both try to elevate the discussion in terms that people understand and give an idea of what a future looks like that includes quantum computation.
Yeah, perfect. I think this ports well into our first question, which is on a broader question for those listening, and whichever you wants to take this one first. This one is for those that aren't deeply in the tech industry, and even for those who are, but maybe aren't super deep into quantum. How would each of you best describe why quantum computing matters and how it will affect both our lives individually, society as a whole? And I know this can go a number of directions, but just keeping it as from that author perspective and helping people digest the information. How would you get both best putting?
One usual explanation you use is that all the stuff we use today is quantum. I mean, all the transistors, the lasers, whatever you use it, your laptop, your smartphone, they all use a lot of quantum technologies, but they use the so-called first generation of quantum technology, the first revolution. It's based on the interaction between light and matter, understanding the energy levels in atoms and electrons and transistors and stuff like that. And so the new revolution that against the name that was created back 21 years ago, the second quantum revolution, we are using new phenomena which were not and are not yet used widely in our digital tools. So one is superposition, the other one is entanglement, which is weird. And the last one, which I find very interesting, is we are able now to control individual control objects, atoms, photons, and electrons. But that's not the use case. So the use case then are multifold because they deal with three kinds of technology domains. One is quantum sensing, which we don't talk enough about, I would say, because there are new generations of sensors which are way more precise and accurate than the existing ones that can be used, for example, in medical imaging. So that's as a practical usage for, everybody in hospitals. There are some companies, for example, who try to make MRI more affordable. That's one example. Then you have quantum communication, which deals with the security and the way you improve communication security. There are many, many options there. And then, of course, we have quantum computing, which is supposed to bring a new level of power for some domains of computing. And that's where a lot of subtleties have to be explained, because quantum computers are not bound to replace existing classical computers, even the largest ones. They are kind of tailored for doing specific things which couldn't be done and can't be done even in the future by classical systems. And one of the domains I like most is chemical simulation, and it's one of the most promising, where we can have real speed up, so real acceleration for computing, making things that are impossible today become possible, and where you can make a lot of inroads in whatever. Capturing CO2, develop new drugs or whatever, develop new chemical processes. There are tons of things that can be done, which may have an impact on people, but probably I would say indirectly. And one example I use is with AI. If I take the example of COVID, when COVID was popping up late 2019 and early 2020, um, most people don't know that AI was very useful to understand the spike protein work in the virus, and then to develop new vaccines. And so AI was used behind the scene. But we got the vaccine, okay, but we didn't know it was built with AI. So I think that many of the things that are going to be done by quantum computers in the future are going to be like this stuff that you don't see, but that may benefit you as a user without seeing the tool. It's a bit like when you use Google Maps on your smartphone. You see the apps on your smartphone, but you don't know that most of the stuff is done on tons of servers on the cloud that you don't see. So it's going to be probably the same for quantum computing.
Thanks, Olivier. Bob, how do you?
The way I think about it is, let's imagine what the largest possible computer is, right? Just not that we can make, but just the computer. And it's nature, really. That is, just as Olivier said, the things in our laptops and whatever are quantum, but it's really everything. It's everything about you. It's every electron, it's every atom, it's every molecule and everything like this. So in some sense, if nature is the computer, you and I are the apps, as well as everything else you look around and see. So clearly this is pretty powerful. And so it makes a lot of sense to try to emulate the type of computing that nature does. And that is, at the very small, something in physics we call quantum mechanics. And it's a very, very strange, bizarre part of physics. It came about starting about 1900 when people started realizing that some of the classical physics, Isaac Newton, their understanding about electricity and so forth, just weren't completely working. There were some odd cases, and that's because it was a model, right? Physics is not truth. Physics, as we know it, is just a model, and we try to match what's happening in the universe to that model. The other model, for example, that a lot of people know about is relativity, Einstein. Well, that's the really big part of physics in the model. Quantum mechanics is the very small. And so that's what we try to emulate. Now, as we developed computing, really starting about the 1940s during World War II, we developed what are called digital computers, binary computers, lots of zeros and ones and things like that. Very powerful. We're all using it right now as we speak. But nature itself is not a bunch of zeros and ones, right? Nature is this other type of quantumness, if you will. So we're trying to harness quantum to do the things that we can't do in the systems, the classical systems, the 0 and 1 systems that we have today. And that's hard to do. That's why it's taking a little while. Olivier pointed out a lot of great use cases, in particular chemistry, new materials and things like this. It's apples to apples, right? So if quantum mechanics controls chemistry, well, we should be able to compute with chemistry with quantum computing. And people started noticing that about the late 1980s. So it's very exciting, and there are roughly 3 classes of use cases, but it's really hard to make quantum computers. And I do want, when people say what's taking so long, it's exactly the point that everything around us is quantum. So when you try to control quantum, the environment, good old nature, keeps messing up our computations. So all the sorts of restrictions and the technologies of how do you control it without errors popping in? How do you make it big enough and things like this? Ultimately come down to this question of how do you coexist with nature, take advantage of nature, but not have it screw up what you're trying to do intentionally.
So to add on to that, I've got a few thoughts. Those were really good answers, gentlemen. Olivia, you had mentioned classical computers being quantum too. And when I heard you say that, Bob, you had brought up the 1940s, and that picture of an ENIAC came to mind. And I started to imagine distances, electronic signals being sent over distances, and trying to keep the signal, remove attenuation, essentially remove signal noise, and then being able to build that digital signal. And Olivia, as you said, it's still quantum, but what we're doing is we're scaling it in a way that takes out the noise in order to make it digital. So classical computers are we've mastered being able to make them very deterministic, if you will, right? And quantum, as we know, as Bob, as you pointed out, from Newtonian physics down to quantum mechanics and relativity, quantum computer is more probabilistic. So you have classical determinism versus quantum probabilism. I think that's a word.
Yeah, it's a good explanation. The I would say that quantum computing, whatever the way you use it, it's analog computing. There are various breeds of quantum computers because you got the D-wave quantum annealers, you've got analog systems from Pascal and QRL, and we've got so-called gate-based programmable quantum computers. But in all cases, we are dealing with an analog system because the famous superposition that is being applied to qubits that are in between 0 and 1. I mean, the way you define the data that's in a qubit is two real numbers, if you want to simplify things. And these are real numbers, so it's analog in nature. And interestingly, when you look at the details, you can get a real exponential speed up when really you can explore the whole space of these values between 0 and 1. Otherwise, you won't have a real speed up. So there's a kind of interconnection between being analog in the way you process the numbers within the computer and the fact that you can obtain an exponential speed up. But then you're right to pinpoint that. Being analog connects you to noise because exactly with the audio system that Bob and I knew in the past before the audio CD, we have noise in quantum bits. And this noise is detrimental to the quality of the results. It doesn't explain why it's probabilistic, because the fact that it's probabilistic is due to something else, which is quantum measurement. But the noise is the pain in the ass for all these systems. That's what everybody's trying to fight. You have tons of people trying to manage a so-called error correction. So they invent new codes, which, by the way, were invented in the past for different domain. The most interesting place where error correction was invented was for telecom, because telecom were using signals over long lines, typically on radio waves or whatever, or 3G, 4G, 5G. And that's the area of the modern digital era where you have a lot of error correction, where you have a lower overhead for error correction for storage, for example, and even for CPUs. I mean, a chip from Intel or AMD has some embedded error correction, but it's used only 1 out of, I don't know, 10 power 18 times. It's very low frequency.
So what I heard is, first off, we just need to reconcile this whole quantum mechanics and general relativity thing. And
it doesn't meet in the middle. Let me just, for the sake of, because we'll probably drop some terms. Olivier already mentioned entanglement, but there's this word qubit or quantum bit. So classically, bits are zeros and ones. The basic unit of quantum information is a qubit. Michael, I want to mess up your head on your last question, because you can absolutely do probabilistic algorithms and heuristics classically. And oh, by the way, all of classical computing can be embedded in quantum computing. So there's not this kind of clear separation. It's just the notion of the purely quantum operations do have probability and some natural randomness. Now, just because we say the word random doesn't mean like we'll get any possible result, right? It's controlled. So when we do these quantum operations, these quantum algorithms, first of all, it's a completely different programming model. You can't copy information, just as an example, right? You can't have a quantum database because the minute you pull it out, it destroys it in the database, right? So the operations in quantum are just completely foreign to anybody who's done classical coding, right? They have to relearn this. So the general process is to set up the problem, perform a number of operations so that the best answer is the most likely one that is computed at the end, right? And if it was deterministic, you'd really be doing something classical. So there's the probability. You may have to run operations or algorithms more than once to have enough confidence to say this is the right answer.
So that's what I mean. People ask what quantum computers are. what I'd usually distill down is the narrative that I was talking about earlier. Classical computing is very deterministic. Input in, you get this, you expect to get the same input out, and you should. Quantum computing, probabilistic. To your point, Bob, you have to run this. You have to run the calculation possibly a number of times until you actually get the error and the measurement that you do want after applying quantum Fourier transforms. So, yeah, I agree with you.
There's one way to describe that. One easy way to describe that is to say that if you execute your quantum code or circuit once, the result is probabilistic. But if you execute it a large number of times, it can be multiple thousands of times, and you make some form of average, then you will converge deterministically to some useful result based on whatever the chemical accuracy you want for chemical simulations or another kinds of problem, like factoring a number. So it's both deterministic and probabilistic. It's probabilistic because the measurement of a qubit that superposed yields a random result. But if you do a so-called sampling and multiple times, then you converge on some deterministic result. But there are the exceptions there because you can embed some randomness in your code. So if you embed some randomness in your code, when you do some so-called mid-circuit measurement, so you do some measurement within your code to drive some random numbers that you use in the rest of your code, like for Monte Carlo simulation in financial services, then you drive real randomness in your system. Non-determinism, and you have randomness. You have both of them.
And I think we have to be actually very careful because there's a tremendous amount of overlap here, right? So classical computing is not completely deterministic. Only deterministic algorithms on classical computers are deterministic. Probabilistic algorithms on, right? Well, let me give an example, which I think will move us to some of the other topics. And this is Shor's algorithm. And so Shor's algorithm, Peter Shor was a mathematician at Bell Labs, now a professor at MIT. 1995 was a very good year for him. In particular, he discovered an algorithm, right? Algorithms are discovered, not invented, by the way, right? They exist out there. We're very platonic about this. And so he discovered that with a properly large and high quality quantum computer that you could factor numbers almost exponentially faster than any known classical way. Now, most people don't care about factoring after high school, right? So 12 is 3 times 4, but it's at the heart of several current encryption algorithms like RSA. And so this is when people talk about the need for post-quantum encryption, right? And things like this. Now, interestingly enough, that algorithm, there are 3 main parts. First part is classical, the middle part is quantum, the final part is classical, right? So just as we're being careful about our language, it's about computing, right? It's about using the right type for the right job to do whatever we want. And everything we really do is mixed.
We'll always need a classical computer in order.
But the way what Bob you just said is true for probably all quantum algorithms.
Yeah.
Most algorithms I know need some classical preparation and need some post-processing. To what extent it's important, it may depend. Typically for chemical simulation, you've got a huge preparation work before doing your quantum computing. And there's mostly, in all cases, some post-processing also involved, which can be probably lighter than what you do in pre-processing. So yeah, you've got some so-called hybrid computing. But interestingly, there's a big confusion in this space, I think, between what we just described as hybrid computing, where you have a mix of classical and quantum computing, and so-called variational computing, which is a different kind of algorithm, where you have a kind of optimization function where you tune your quantum circuit, you go back and forth between the classical and the quantum part to find some optimization, some results, and it's a different thing. But maybe it's too complex for our audience.
CPUs, Bob, I saw that you had written an article recently, and I was going to poke you for a little moment, Tizia, but to Bob's point,
I so dislike this word hybrid. It's so damn cheap. It just means, hey, we're using 2 things together. It's hybrid, right?
I remember my 386DX coprocessor, and I was really excited about it.
So this computer, my desktop computer, it's got a GPU in it, a CPU and a GPU. It's hybrid, right? it's all of computing is hybrid. All of computing is heterogeneous, made of different things. And so, the fact of the matter is, and I think this is a really important word, is practical, right? Everything we're after, how long it will take, right? And things like this. Google has an example of it will take 47 years on a classical computer versus very brief time on a quantum computer to do an incredibly useless problem. Now, I'm not going to wait 47 years on a classical computer for totally useless problem.
Maybe they just haven't found a use for the useless output yet.
No, it's random. It's actually random. Going back to our discussion.
There's no input data in that
Keep going
benchmark,
on this
so
one, Bob,
it's
'cause
useless.
important
That's why
actually
it's
to the next
useless.
question.
Yeah. So now, there's certainly good science underneath there that shows other things, but I think what we're all after is the practical use of quantum computing, right? Not just these exotic lab experiments, right? That no one understands, no one knows the value, if there is any, right? And when are we going to get this? And how much will people make based on it? And how will our lives change? And
with your work, Bob, at IBM Research and just both of your decades of experience, how do we see the evolution of quantum computing moving in, the next 10 to 15 years? And obviously we don't have a, magic wand that we can wave, but specific to the accessibility for those that don't have access to quantum computing and the leverage of what it will be able to do in the coming future, and then specifically practical application that is a little bit more near and dear to people's hearts than a random problem that is 47 or half century out. If you guys could touch on this based on maybe some examples, this would be great, or even just your opinion on it.
So here's one. So I was just talking about practical computing, and we talked about qubits before, and what flavor of qubits, physical qubits, logical qubits. We can get into terminology all we want, but let's just start with whatever qubits are, however we implement them. We're going to need a lot of them. We're going to need thousands, tens of thousands, hundreds of thousands, millions, depending on what flavor you're talking about.
Yep.
I listened to a presentation this morning where somebody's very proudly talking about their 9-qubit quantum computer. Right. So let's just pick 100,000 as a nice big number somehow without getting into the details. So many of the providers have a few dozen computers, qubits in their computers. IBM went up to a little bit more than 1,100. It's dropping down to about 150 and networking them and so forth like this. But whenever we're discussing these things, right, we need 100,000 and you're telling me about your few dozen. Like, how do I go from one to the other? And it's not a manufacturing problem. You just say, well, we'll just make a whole lot more, right? And we'll stick them together. It's not like adding memory in a computer. You put something in
noise
the slot.
scales as well.
Oh yeah, noise scales and all sorts of ways and things
Noise
like
scales,
that.
computing skills. Yeah.
So however many
nature doesn't want us to build one.
well, we have to get smarter. So the idea is that there's some limit, right? In one unit, which we'll call a quantum processing unit, there's so many qubits we can jam in there. And it could be a few dozen, a few hundred, a few thousand, whatever, but there is a very practical limit that is well short of 100,000. So you have one of these, you have to connect them together. This is the point. You have to network them together, and you have to do it in a quantum way. Yeah, it's not just running a little wire between them. You have to preserve all this quantumness, and you have to build bigger computers from these smaller units. And this is what we're starting to see. A lot of companies won't get there. A lot of companies will not be able to figure out how to scale. And so over the next few years, unfortunately, the quantum landscape will be littered with these tiny quantum computer companies that never managed to jump out of these small ones. Full disclosure, I'm on the board of a quantum networking company called New Quantum in the UK, but other people are doing this work. IonQ announced some work in this way. So the next big thing is the practical use of quantum networking to build larger quantum computers from smaller components, right? And control them well with low errors and do all the extra stuff. So this is the big thing. And this is what I would say is the hallmark of this second phase of quantum, where the first phase is just creating a bunch of qubits that all kind of work together, right? Yeah. And if we don't get that right, then we're dead in the water.
No, that's nice. Olivier, anything to add on that one?
I should separate the problems. I mean, one challenge, which depends on the kind of qubit we're talking about, is to scale as far as possible before requiring this interconnect, because this interconnect is a pain. It's going to be painful to make that work successfully. I think it's even harder than have multiple qubits connect to the other, because there's a lot of overhead. We're not sure about the efficiencies, the noise it brings. It's going to bring new problems for compilers, because they will have to address a limited connectivity between multiple processors, quantum processors. It's going to be very difficult. So one challenge, which is how do you increase the number of qubits in a reliable way? So how many qubits will you have in superconducting qubits, in silicon qubits, in photonic, whatever? And then how do you manage the connection, and what technology? Because if you take IBM's roadmap, for example, they have, interestingly, multiple options to manage this connectivity. One is to use, I would say, close range microwave guides, which is kind of, I would say, credible. It's possible to do that. It avoids having too large circuits, so it limits the crosstalk between the qubits, but still you can have neck-to-neck connections between the chips. But then when you extend the connection to a longer distance, you're going to have multiple flexible cables using those microwaves, which have losses, so it drives some problems. And then for longer range and higher capacity, you will need the photonic link that Newcomb and WeLink and IonQ are working on. So we're going to have multiple levels of problems. And so what I think is very important, at least for the midterm and for the early stage of so-called fault-tolerant quantum systems, is how far can company go without resorting to these, connectivity solutions, and then how are these connectivity solutions will compare with each other, and how are they going to work efficiently? So it's, it's typical from this quantum world where we live here. It's a weird place where you have multiple technology problems, which mix, I would say, scientific and engineering problems. Sometimes the weight of both is not obvious to understand if you are external to this world. I view that it's always a mix of them. It's not just, okay, we're going to do some engineering and put brute force and it's going to work. There's a lot of science, a lot of experiments, a lot of theoretical work to do, both hardware and software and physics. And that's why it's a long journey. And it's the passion I have for this field is the diversity of the technology solutions that people are trying to build, the human creativity that you have in this world. That's the reason why it's very hard to plan what's going to happen, because there's so much combinations of technologies, so much diversity.
Even more, I mean, science is a big part of it. I would, so someone made a dumb comment about 5 years ago about quantum computing, that it was, all that was left was engineering. Like,
I hear that a lot.
I know, and it's so naive. There's a lot of science, but there's a tremendous amount of engineering. So, Olivier, what I was thinking about as you were speaking was the trade-offs in engineering, right? You can have a little bit more of this, but it suffers over there, right? So reaching this right optimized balance of the factors. And there are probably 6, 7, 8 different ways of making these qubits, by the way, right? And so to think that maybe the world is just going to use one type is completely wrong. So this is what we're learning, right? Yeah, absolutely. We're learning more of these things, but all these terms, good enough, big enough, require definition.
Yeah, speaking of terms and acronyms, obviously in today's climate, AI is probably one of the hottest topics around in both the tech world and then just taking the whole entire world by storm in terms of uh, people touching it. But I'd love to hear from both of you how you both see quantum computing intersecting with AI, and how that combo could unlock more than we're able to achieve with classical computers today. And I'd like to start this one out with Bob kicking this one off, because both of you have been involved in with your work, Bob, at IBM Research. You've been working on AI way before it was ever an acronym in the back of people's minds. So I'd love to hear both of your takes and perspectives on this, because it's going to be important as it ties in, but just equally in its own right. So take it away, guys.
Conference that Olivier and I were at, the Insight Quantum Technology in New York a couple of weeks ago. I started out by saying, well, if you're doing just quantum computing, you have a 20% chance of getting a grant or getting venture capital funding. If you throw in AI, you have 40%. If it's generative AI, you have 80%. And by the way, if you do it on the cloud, or for you guys, blockchain, you 100% chance of doing this, right? And the real case is that even last quarter, the private investment in AI was 11 to 12 times more than it was in quantum. So you'd be a fool if you had a quantum computing company and didn't mention AI, right? Just for the sake of survival and think that it's worth. I see that there are three applications of this, three ways in which it's used. So the first way is right now, there are a lot of algorithms in machine learning. People may have heard of the transformer method used in generative AI. They're named ways of doing certain things, right? Can we do similar things, similar algorithms, or different algorithms, but to achieve the machine learning results? Quantum for AI. Now, there are a lot of problems. Neural networks do not translate directly. Olivier mentioned something called variational, which comes from a deep physical concept and things like this. Very noisy, fuzzy. People love to talk about this, but the core problem is whatever advantage the algorithms may show, you simply cannot get a lot of data into the quantum systems to do valuable AI. It just takes forever. It's literally exponential to take the classical information and make it in a quantum form. So people like to talk about their wonderful algorithm, but the first step is actually impossible. But let me tell you about the second step, right? So it's research. It's going to take a little while. Second area is using AI for quantum. So we've talked about noise in different ways like this. If you keep doing a circuit, operating, you're running an algorithm and things like this, you can see what the results are like. You can put various tests to understand, can we use AI to actually decrease the number of errors that are happening in this, observe the patterns, kind of remove the problems. It's not an exact example, but if you think of noise canceling headphones, right? So how do they work? Well, you have music, you have a book or something you're trying to listen to, but there's outside noise. And so what they do is they subtract the outside noise and then smooth it out a little bit. Well, make it more sophisticated, use AI for that.
In inverse wave, yeah.
Yeah, it's a similar way. And then the final, and let me say grown-up IT way of looking at this is to say, why do we keep focusing on these algorithms? In the real world, we have workflows, right? There are lots of steps to computations, to solving problems. It's not just one thing you do. And for chemistry, earlier, Olivier, you were talking about, you might do an HPC thing to actually get some parameters, some interesting information about a chemical process. You might then feed that information into a quantum process to compute something, and then you take the output and feed it into AI and repeat as rinse and repeat, as they say. So it's the right type of processing, classical, traditional classical, deterministic or not, AI and quantum for the right part of the job. And that's the correct way, I believe, to think about this. Don't glom everything. Don't just think it's, we stuck them together in a hybrid way. Separate them out. Real people, real businesses use workflows. And I think the sooner people understand that, the sooner they'll know where quantum actually and AI can actually have value for them together.
Great. Thanks, Bob. Olivier, anything to add to that?
I see, of course, potential quantum machine learning or quantum AI being quantum algorithms for AI, which is not very, I would say, popular right now because it doesn't scale well, because you have these data loading problems. And there are a lot of things around that. So around any quantum algorithm where you got AI. So I think that we have kind of machine learning which prepares the circuit, or which prepares how you load data in a quantum circuit. So typically a variational quantum algorithm, it can be anything. It can be even, compilers, which are preparing the gates that are being used by the system, use AI at this point in time, because optimization use machine learning. Then you have the stuff you do after your computing. For example, noise mitigation is using AI, is using machine learning. So it's after your computing. But other stuff happens. For example, Google in the past and others are using machine learning to optimize the hardware itself, regardless of the algorithm. So they optimize the frequency allocations for the qubits, for example, because you have to manage it so that there are fewer interferences between the qubits. And then I put, I would say, Gen AI and LLMs on top of that, because it helps people do their work. I mean, it can help generate algorithms or circuits as well, but it can maybe just do your work as a teacher, a student, a researcher, an industry vendor on a daily basis, like your mail, or your search engine. And what I discovered in the last year is the power of that. It's unbelievable. I mean, it's unbelievable what you can do with ChatGPT right now, or with other systems like Google Notebook LM, which can help you exploit existing documents, even with explainable AI. So I think that the power of AI for quantum is huge. It's enormous. The power for quantum for AI is probably in the making. It won't happen soon. So it's an unbalanced situation. Quantum for AI, so. AI for quantum, yes, definitively everywhere.
If I could just make one point, because I think we've been implicit about this. We mentioned it a couple of times. So when you think of AI, right, maybe you think of ChatGPT, some other applications and things like this, but you're using software, right? And we think of data and software and things like this. Now, on the other hand, you hear about NVIDIA, the world's most valuable company, and you hear about GPUs and Blackwell and Hopper and things like this. So people do have at least some sense there's hardware underneath. Turns out there's much more even. I mean, the way people are building infrastructure and memory and storage and things like that to support AI. So it's accepted that AI is hardware and software. The quantum people, for the most part, only talk about hardware. Now, we've talked about algorithms, which are software, but we haven't been that explicit. Olivier mentioned we need better compilers. That is, we need better software tools.
Yep.
And the only way we're going to get to the point where quantum is really useful is if there's at least as much solid work on the software side as is going on in the hardware as well. So and that's where I think a lot of the interesting work will be done.
On that, I was trying to, as you guys covered some great points. That's difficult to add anything onto that. But when I get asked this question, I'm always of the opinion that AI will complement quantum more than quantum will complement AI when you're trying to find solutions. For example, be it whether or not different ways to, maybe there's something more. There's Shors, and then there's derivatives of Shors, and there's different. Maybe there's a better algorithm that could be one that we haven't imagined that AI could discover. Maybe there's engineering things that it could solve, manufacturing processes of qubits, the correct type of qubits, be it trapped ions or photons or whatever it is. Maybe it can come up with something in a way that, using information that everyone knows, but connecting dots in a way that nobody statistically over this amount of time just hasn't imagined yet.
It's just knowledge management to some extent.
Or finding patterns. I mean, really at its heart, a lot of machine learning is just observing. And can quantum help find better patterns?
The challenge is to not draw lines where there are no dots, right?
Well, I've actually read an application the other day, and somebody was they were doing a mapping application, right? And they were using AI. And the idea was they took an actual city grid, right? And, they were optimizing using AI. And then they just put in some detours, right? Closed down some streets. And the AI got totally screwed up. And when they went under the covers, AI had invented new roads that went up in the sky and over and down and things like that.
Oh, and three-dimensional.
That reminds me of the MapQuest days back in the day. It'd be like, don't drive off this bridge because it tells you to. But
hallucinating new roads.
Yes.
But that's interesting because the data set was probably put in a two-dimensional way, but then the machine, maybe I'm extrapolating efficiencies that AI might drive in the future, in that, hey, we can instead of putting all these qubits two-dimensionally, let's start stacking them. Oh, and wait, now I can superposition and entangle them more efficiently using 3 dimensions, like something similar to that. I'm sure that specific scenario has already been talked about, but connecting things that we already know, taking ideas we already know, and then Olivia, I can see
two
you
scenarios. I have two fancy scenarios that I love.
Yeah.
One is I put in Notebook LM a couple of documents on a weird field from quantum physics. It's called quantum foundations. It's kind of a mix of philosophy and physics. It's a domain where you have niche. So a lot of niches. So people believe in this interpretation, that one, that other one. There are about 12 of them around, but they don't talk with each other. They each are in their own turf, I would say. You put that stuff in the system and you ask them, do me a comparison. Nobody has ever done a comparison, and you get the comparison. That's amazing. I mean, the other thing is you can ask an LLM to find white space. I love that. So what's missing here? That it's so powerful to find missing stuff in documents, in reasoning. I even tried a conjecture, stuff like that. So
Yeah.
it's something that's empowering people who have good questions, I would say. So the way you can be upskilled with AI or these systems are LLM based, you need to learn about asking questions. If you know about asking good questions, you will get good answers, maybe with some mistakes that it's up to you to find it. But ask the right question is going to be the key success factor for anybody. I mean, whether you're a developer or an architect or
But that's half the
salesperson,
problem.
whatever.
That's half the challenge
Yeah.
is finding the
Find
right
the problem,
question
find
to
the
ask.
questions.
Yeah.
Google offers a 10-hour course through Coursera about prompting. I don't know what the heck they need 10 hours for. I do want to just give a note of caution here, which is I think people are way too generous about generative AI in particular, right? You tell them it made a mistake and a hallucination, whatever, and they say, oh, don't worry, it'll get better. You know, it's like, yeah, I hope so. It will just be that the mistakes will be harder to find.
Yeah, I'm very actually worried about this when AI LLMs start to become the source of truth.
Surgery, right?
People
Next time it'll be better.
make mistakes as well. I mean, anybody makes a mistake. I mean, the way to compare an LLM with people is it like a bad student or a bad teacher? It's a joke within the academic world.
Bob, I'm going to challenge you with a question. You say it's going to get better, and when I hear that, my first question is better for who?
Yeah, no, I know.
Because at the end of the day, we all have our own goals and wants, and you never really understand someone unless you know what they need. So that means we're agenda driven. So better for who? But anyway, I get
yeah. So
Well, the battle. Yep. The battle is old. I mean, it started in the 50s. It's the battle between the so-called symbolic and connectionist AI. So how do you put some reasoning in those systems, which are most of the time probabilistic? So LLMs are probabilistic. So the fight that is fought by guys like Yann LeCun in Meta and Facebook is how do you embed more reasoning in those systems? So you have chain of thoughts, you have agents, stuff like that. There's not a single way to embed reasoning in the system, but it's going to be a word like Bob hates. It's going to be hybrid.
As a segue here, I think it would be good to pour it into letting each of you before we wrap up. Give everyone in the audience a little bit of sneak peek at each of your books. Give us a little minute of what we could look for, and what we'll do in the show notes at the top is we'll leave links to both of those. So, Olivier, if you want to kick it off, talking on understanding quantum technologies, and then Bob, you can wrap it up for us, talking a little bit on dancing with qubits, and then we can close out this first QA PQ panel.
Okay. So the book is open source, so you can download it for free. It's a very large piece. It's 1,500 pages. It covers, I would say, everything I discovered on my own. And I'm an IT guy. I come from the classical IT world. I worked on AI before. So I was willing to share what I discovered over time in 6 years of time. So I went through all the aspects of quantum physics, history, then quantum computing, the basics of the mathematics that are behind this, then hardware, software, algorithms, use cases. I even cover telecoms, sensing, geopolitics, what the countries are doing. I even have a fancy stuff. I talk about stuff from Star Wars and Gladiator. There are some Easter eggs in the book. And then I'm covering also the quantum fake science. There was a dedicated book from Chris Free on that, but it was in my book for 6 years now. So just explaining what people are using to game with quantum, with fake quantum medicine and stuff like that. So it's very, it's like a sum of many books, but it's not just a sum because they are all connected, because there's a common glossary. All the terms are connected. It's a kind of repository. Some people say it's a Bible. My answer is it's not a Bible, because usually Bibles are not updated. And I update my book every year.
Great. Well, we'll have the link directly in the show notes. Bob?
Here's my prop.
Perfect.
It's called Dancing with Qubits. It's a slightly strange name, but as I mentioned, it has to do with this notion of entanglement of qubits and how algorithms work. Qubits come together for a little while, then they separate and so forth. With a subject as difficult as quantum, it can be very scary to learn. It includes concepts like probability, as we've discussed. It includes complex numbers, the square root of -1. It includes multi-dimensional spaces. And so you might look at this and say, how am I ever going to get into this? I don't remember math, right? I don't remember maybe high school math, or even if you did some sort of computational science in college, you may have gone off and life called and you did other things. So I start with basic principles of everything you need in what people have termed a very comfortable way. It's as if I'm standing next to you, right, on a whiteboard or blackboard. And any sort of confusing bit, I help you through it. I let you know why it's there. So I do a complete exposition of the basic concepts, talk about qubits, 1 qubits, multiple qubits, all of the standard algorithms, but fill in the details. And then I end the book with 2 new chapters. This is the second edition. The first is about the sorts of things we can do today with noisy quantum computers, which are all of the computers today, give you an idea of what they are. And then I talk about quantum machine learning, the state of the state, which needs work, as we've discussed. So I mentioned a little bit of physics, but only enough to motivate the discussion. And I try to keep it a little bit more on the math, well, very much more on the math side, but to give you a good, comfortable background so that you can then read more advanced texts or papers or things like that. So it's had very good results, and it's available on Amazon.
Awesome. Well, guys, I know, as I mentioned already, we have a list of questions that we'd still love to get to. So we're definitely going to have to bring you both back to do a continued. I feel like we could jam on a number of these things and in detail, everything from ethical challenges to what our organization's doing right and wrong in terms of the quantum tech with that upcoming. But first off, myself and Michael, we appreciate you guys both joining us from different parts of the world and enjoyed this conversation, and have a great rest of the day. And we look forward to the next conversation. And thank you again for your continued work. And we hope that everyone in the audience now has 2 other new rabbit holes to go down with checking out your work until that next episode. Thank you guys.
Yes,
we
thank you
appreciate
guys.
it.
Thank you so much.
My pleasure.